Hello everyone and welcome to our webinar about ColdStream NXT for computer hardware. I am Bix and I will be your host today, together with my moderators that will follow along. But to give a quick introduction for myself, my name is Bixant. I'm an application engineer here at Diabetics. But before that, I was a software engineer. So I worked in the backend of ColdStream. I worked on the optimization algorithms to make the code more efficient and so forth. But today, as I said, I'm an application engineer. So now I work together with clients to see what is technical feasible in the realms of generative to enable them with some algorithms from our software. Today I'm going to talk about ColdStream and diabetics in a quick introduction. Then I will give you some pointers about heat management in CPU coolers and computer hardware. And then we're going to go more in depth into a more practical use case for a CPU cooler we did, a liquid CPU cooler. Then we have some time for questions. And in the end, I will point you to some resources and some links to get acquainted with our software and to maybe get in contact with us. If you have any questions in the meantime, by the way, you can always put them in the chat and the moderators will answer your questions. I wouldn't be here if the problems in the world wouldn't get way more complex. To give you an example, for example, you make a heatsink, you need to design it, you have a certain amount of pressure drop you have available, you have a certain amount of heat peak temperature and variance you want to achieve. It's very difficult, but after a few months you iterate, and after a few months you get to a final design. This design is barely good enough, it works, you did a lot of effort in it, but then your boss says, okay, now I need the same design, but with half the pressure drop. Then you have a problem. It's those kind of situations, this kind of pressure that's really happening in the industry right now, is a lot of pressure is on engineers to design better and quicker. And we really want to enable those engineers to design smarter as well. So we provide some smart algorithms to design better and beyond human capability. Especially in the realm of 3D printing, this is a very hot topic at the moment. It's very difficult to design with your own human bias. So, for example, in 3D kind of ways, ColdStream is way better at it because it's algorithmic. But ANSYS and Hexagon saw our company and thought it was very useful, and that's why they are our technical partners, which means that our software actually integrates with the tools of ANSYS and of Hexagon. So we have a collaboration there. To give you a quick overview of a normal conventional design cycle, you often start from a scratch, a blank space. Then you design an initial CAD geometry, for example, pins, fins, something on those lines. Then you start to simulate in your CFD work. It takes a few days, hours to get it simulated. Then you do some post-processing, you need to get the data, you need to visualize it, and so forth. Maybe also some testing, some other visualization, post-processing steps to really get the results. And then you probably will see, okay, the pressure drop is too high or the pressure drop is too low. We have some hotspots here and so forth. The flow is blocking here. Then you need to iterate on that design. You need to make it better. And you do this process over and over and over again, which can take weeks, months, sometimes even years to get to a final design that meets your criteria. That is what you see at the bottom. But we at ColdStream want to do it a different way. We want to parallelize this process, make it a little more streamlined. And that's where the concepts come in. So in ColdStream, you start with an empty space the same way, but you can quickly generate the concepts you would do in serial, you can do in parallel. So in ColdStream, you generate a lot of concepts at the same time. You evaluate them with a performance value. You choose one or a few of the best ones that look the most promising. And then you can eventually, if it's not good enough, then you can also make it even better with the generative AI. But sometimes we see that the concepts meet the criteria and has a really quick way to get to a good result. Today, I'm gonna really focus on the concept generation part for computer hardware. And yeah, we're gonna go a little bit deeper into it. But before that, to give you a quick overview of ColdStream itself, ColdStream is very easy to use. So it's very similar to a CFD kind of package, but you don't need to be a 20-year veteran of CFD experience. It's useful, but you don't need it. I think it's often a day of training and you're up and running with ColdStream. How does it work? You first need to upload your CAD files. So that's the same thing you would do in a CFD program. Is you have your CAD files, you upload it to ColdStream. ColdStream will then split it up in different regions based on your different regions in your CAD assembly, your step files. Then you need to set, similar to CFD, your materials. For example, we have a copper heat spreader here. We want some coolant in the fluid domain, and we want the housing to be from aluminium. So you need to set some material properties and so forth. Then you need to set your boundary conditions. Same thing as CFD. For example, here we have a CPU cooler, so we need to set a heated wall for the Intel chip. Or we need to set some pressure drop inlet conditions for the fluid domain. So for example, here we have some kind of amount of flow in the fluid, so we need to set that as a boundary condition. Then at the end, this is the only main difference between a normal software and ColdStream, is that you need to set your constraints and targets. So in this case, we want the peak temperature to be as low as possible, the variance to be as low as possible, all within the constraint of the pressure drop we have. That's what you set here. For example, here is the temperature targets you set, and here you set the constraint of the pressure drop on your inlet. Then you just hit the button and ColdStream will generate a lot of concepts, hundreds of concepts in a few hours. You can see it, you press a button, you can go get a coffee, and when you're back, you already have 1, 2, 3 designs ready. These designs you can just download at STLs or step files. Another constraint you can add in ColdStream is that you can constrain the problem to the manufacturing type. So for example, if you want to manufacture the heatsink as a CNC kind of way, you can do that. You can also do it radially if you want. Then you have the die casting option, if that's the way you want to go. We also have 3D printing and we have sheet metal. But as you can see, you have control over every parameter of the manufacturing process. So for example, in CNC, you can set the minimal feature size, the minimal angle that your CNC can make. You can also set the spacing between your design, for example, fins and so forth. So you have really control over the manufacturing process, and this you can give as a constraint, as you can see here, is that the design will look different if you have different manufacturing settings. But now we're gonna dive a little bit deeper in the case study itself, which is a CPU heatsink, a liquid-cooled CPU heatsink. So here the heat source was 250 watts, which is the Intel chip. And the objective was to minimize the temperature, the peak temperature actually. We also have some coolant here in the radiator, which is water glycol. The only constraint was that the pressure needed to be below 11 kilopascals. We also see that the heatsink should be made of copper, which has some material properties here. And to give you a quicker, better overview of the case itself, you have an inlet here, you have an outlet here, and the original design was only just a little slit that splits the flow into the two different areas. To dive into some results here, these are the 3 concepts we generated with ColdStream as a reference with the fast concept generator. And we see here that the pins actually cool down the heatsink quite well, but you see that the cooling effect is a little bit local here, and you have a large hotspot here. So you probably know that in CPU coolers especially, but also in other areas, a hotspot is not good for a CPU cooler, because if the CPU has a hotspot, for example here, the whole CPU will actually throttle. So you also want some heat variance to be very even, very spread out. So the same thing with the fins, it cools down quite well. You see here everything is blue. You have some deep blue here, so it cools very well locally. But we see that we have some hotspots in the back here. So the same thing as here, this CPU will also throttle. But we have also another option, the other concept we generated, which is a gyroid. The gyroid structures are actually quite good to mix the fluids, like I said, the same thing as the pins. But also they're very good at distributing the heat, like the variance over your CPU. So in this case, this is the best concept out of the three, because you see that this red is actually lower than this hotspot. So this means that this temperature is better spread out over the heatsink, which means that this CPU will run better than this one because it doesn't have a hotspot that makes it CPU throttle. But of course, if this is still not good enough for you, if the target is not is even like lowering the temperature even more, then you can go to the generative design side of ColdStream. In this case, we have also 3D printing, the same thing with the gyroids. But now the design, or like ColdStream, has a full design freedom of making a heatsink. So you see here that it came up with something very smart. It's trying to make the fluid go over the whole area with these channels, but also introduce some bypasses to fix the hotspots at the end, which in this case, this here is the outlet. So it tries to cool down the whole CPU like the pins and the fins, but it also has some bypasses so that it doesn't have some fresh, cool water also flowing to the outlet, so you don't have the hotspot. But in this case, you see that it's actually quite a good solution because the temperatures are really low and very even. So in this case, a generative design is actually way superior to a normal conventional design. To go a little bit more into detail into the actual data which we gathered, is that of course when you need to increase the flow rate, you always will increase the pressure. So this is the price you pay if you want more pressure or more flow rate. You always need more pressure. So that's this graph. But in this graph, we see something that is very logical, but you need to think about it a little bit. Is that, for example, at low flow rates, the fins are the best solution. This means, and it's very logical, that fins with low flow, with low pressure, they have a lot of contact area. So in thermal situations, it's always better to have the lowest contact area is the most contact area, sorry, has the best cooling capacity. But we see at a higher flow rate, if the fluid doesn't get that much time to like really absorb the heat, then pins do way better because you want some mixing in the fluid. So this is actually will overtake the fins design at some point if you have a lot of flow rate. So like you see here, the fins are quite good, but at a certain point, the pins with their mixing is better than a normal fin design. But of course, you also see a difference between the gyroids and the pins. Gyroids are actually the same mechanism as pins, but they have a lot of surface area, first of all. And second of all, they also have the mixing in a three-dimensional way. So this means that the gyroids actually perform a little bit better on just the temperature, for example, but also way better on the variance. But on temperature, they also perform a little bit better than the conventional pin design. But now I'm also going to show you the case in ColdStream itself and how easy it is to set up. But of course, you see here we have a demo account, which also has some other applications. So for example, we can also do naturally convection, like forced or natural convection cooled cases. We also do electronic cooling. We do motor cooling, which is more of like a radial kind of thing. Cooling sleeves, two-phase, inverters, and so forth. So you have natural convection, you have forced convection with fans. But in our case today, we're going to look at the liquid CPU cooler, which is of course, liquid cooled electronic chip. But this is the view you would get in ColdStream, and you can see that every one of these lines is a design run. So you want to try something different out, a different shape, or do a simulation. Every one of these lines is a separate run. And as you can see here, we have the standard design modes, we have the simulation, but we also have the generative design mode. But the simulation is just a CFD, similar to a CFD, but then in our software, which is way more easy to use than a normal CFD software. But today we were talking about the concept, which is the standard design here. Also, you can choose, for example, in the standard design and the concept generation, between CFD based, so that then you want to compare every result based on CFD. Or you can do the fast concept generation, which is based on correlations. Correlations are the 1D approximation I talked about. Just a quick way to really get a good result and compare different designs together in the concept phase. And the main advantage is that they only take a few minutes to generate and to simulate actually. But to look at a setup in ColdStream, this is the view you would get. And then you will continue by starting your case. And this is the case we're gonna look at today. But now I can show you a little bit in more detail because it's in 3D. But this is actually the same files you would get as in your CAD software. So the first step is to upload it. That's where we're at right now. These are the different areas you defined in your CAD software. For example, we have the copper heatsink at the bottom. We have the fluent on top. So this is where the coolant will flow. And then we have the housing. And like I said during our presentation, you need to set up some different things. You need to set up the material. For example, here you can click this button. We have some predefined materials, but you can always make your own by just giving it the material properties here. So you need to do some setup in that regard. So you need to set up the materials. For example, here you also see that we have the Intel chip. In this case, we molded as a heated wall at the bottom, which a certain amount of wattage it's producing. Then we also have the coolant here. So then after you set up your, you uploaded your CAD file, you set the materials, everything is ready to set up your boundary conditions. So here we have, for example, the inlet, and we want that the inlet is a certain amount of pressure. So that's here. But you also need to set, for example, your targets and your constraints. In this case, we wanted to optimize the heatsink so that it uses the same pressure drop as the reference. And we wanted to optimize for temperature minimization and temperature variance minimization on the heat, on the chip here. Then, of course, one thing that's very different to CFD and CAD software is to set up a design region. So here we have the fluid, and we want to design a heatsink in the fluid. But we don't want the heatsink to come into the inlet and outlet areas. So we define a sub-region of the fluid. So as you can see here, you have the inlet, the outlet, this is the whole fluid, but we only want the heatsink to go in this part of the region. Then in ColdStream, you can select your manufacturing type. In this case, we can do, for example, CNC, the pins and fins, and what I talked about, but we can also take some more complex shapes like the gyroids. And if you really want, you can do the die casting and the sheet metal as well. So for example, we take these two shapes, we want to compare them and find the best parameters for each of them. And here. Then you have also the settings for your manufacturing type. Same thing, we have some predefined 3D printing settings and so forth, but you can always input your own manufacturing constraints and your own manufacturing settings as well. So 5 minutes later, we have our whole setup and we can just run the case. So this is how easy it is to set up a case in ColdStream. To show you some results, for example, this one is finished. You'll get a little bit more data. This is just a quick overview of a summary of your results actually. But if you want to go into more detail, you can go into your tables. And here you see the different iterations. But here you can really go into detail. For example, you can see all the temperatures. You can see the velocity of your inlet, your temperature in the inlet, the pressure, and so forth. But what I find a little bit easier to use is the design evolution page. And this is really what ColdStream is, a visualization of what is ColdStream trying to do. So here you see that there is a performance value. This performance value is based on the constraint and the target we set. So here we set a temperature minimization target and a pressure constraint. These two combined will give you this kind of graph. The lower the performance, it's a little bit counterintuitive, I know, but the lower the better. Then we see that there is a number. This number says, okay, ColdStream is generating designs. Then the difference between blue and green is that blue is a feasible design and green is a best design at that moment in time. So of course, the first one was the best because it was the only one. Then this one was not as good, so it's blue, same one for these. And then here it found a better one. This process will continue and you see that it actually quite quickly converged to something which it thinks is best here. Every one of these circles is a design. So if you take, for example, this one, you can see here that it generated these kind of pins with these parameters. But of course, we can take, for example, a very bad one here. It tried to generate other types of fins. Yeah, of course, this one doesn't work because it has less pins. But if you can go to the more optimal one, we see that this is the most optimal design. As you can see, you can have hundreds of designs in a matter of hours. If you click the button, you go get a coffee and come back, you will have at least 3 of them already. So that's how quick this quick estimation mode is. Then you can quickly by hand go through them or just choose the best performing ones. Choose if the design is good enough, or you can even improve the design with generative AI if it's not meeting your criteria. So if there are any questions at this moment, please feel to put them in the comments and the moderators will answer them. But that's really it from me today. If you have any other questions or you want to see ColdStream on your own computer, you can access our viewer account. You can just play around with the buttons and everything I showed you today. But if you want to have an insight in your application, if something you have is interesting and you want us to look at it, or you want more information of ColdStream itself, you can always reach us at these contact information. But my time is running out, so thank you for your attention and that you joined our webinar, and hopefully we will see you soon in another webinar or in person. Okay, bye-bye. Thanks for joining.